Hello. Today we are going to do homework 2. It's pretty much to do 6 exercises totally. And in this video we are going to do the first and the second one. So let's start. Exercise 1. We get some information in the start, so let's put it into the text here too. If x1, x2, xn are numbers or random variables, then the sum of these are, and this we know, sum equal 1 to n xi, which can be expanded to be x1 plus x2 plus ... plus the last one, xn. That's the sum. And in this exercise we shall use this information, and we shall use also that let a and b be constants in this exercise. Okay. A. Show that the sum I equal 1 to n axi is equal a sum e equal 1 to n xi. Okay, we have to show this. We have to start with what we get, and what we get is this: sum I equal 1 to n axi. And then we write this out just as above, but this time when I is equal 1 we get ax1, and when I is equal 2 we get plus ax2, and so on, plus ... plus axn. And here we can see that we can factorize a outside a parenthesis like this. And then we get what we are going to show, because what's in the parenthesis now is just the sum of the xi's from I equal 1 to n. Exercise B. It's pretty much the same, but here we are going to show that the sum I equal 1 to n xi plus b is equal the sum xi I equal 1 to n plus nb. Okay, again we have to start with what we get in the text, and that is the sum I equal 1 to n xi plus b. And we can expand this and write x1 plus b. That's when I is equal 1. But then we're going to let I be 2. Then we have to write plus x2 plus b this time. And then it's x3 plus b, and so on, until we get the last one, xn plus b. And rearrange this, we get x1 plus x2 plus dot 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 plus xn plus b plus dot 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 plus b. And we see that this first x1, x2, xn is the sum over xi, I equal 1 to n, and the last b's here, that's actually n of them, and then it has to be n b's or nb, what we was supposed to show. Let's then go to C. And in C, it's again pretty much the same. So it's good training. Show that the sum over xi divided on b from I equal 1 to n is equal 1 over b times the sum I equal 1 to n xi. We start with what we get, that's the sum I equal 1 to n xi divided on b. Then we expand, we rewrite the sum in all its terms, so we get x1 divided on b, and we then let I be 2, then we have to add x2 divided on b, and I could actually write the next one is 3, so then x3 divided on b plus dot 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 plus the last one xn divided on b. But then we see that 1 over b is in all the terms here, so we can factorize this outside a parenthesis. So I get 1 divided on b, parenthesis x1 plus x2 plus x3 plus dot 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 plus xn. And then we see that all in this parenthesis is actually just the sum of the xi's from e equal 1 to n. And this was what we was supposed to show. Okay? So let's do the last exercise. D. That is show that the sum I equal 1 to n axi plus b is equal a sum I equal 1 to n xi plus nb. So let's start with what we get. I equal 1 to n axi plus b. And then we rewrite this sum as first, when I is equal 1, we get ax1 plus b. And then, since it's the sum, I have to add the next term, so plus. And the next term is when I is equal 2. And when I is equal 2, we get ax2 plus b. And so on, until we get the last term, when I is equal n. Then we get axn plus b. And rearrange this, we get ax1 plus ax2 plus dot 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 plus axn plus b plus dot 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 plus b. And this first n terms, here we can factorize a outside, so we get a parenthesis x1 plus x2 plus ... plus xn. And in the end we have all these b's, which is actually n of them. So we have n b's. And now we can see that what's inside the parenthesis is just the sum over the xi's. So that we can write like this: the sum of the xi's from I equal 1 to n plus nb. What we was supposed to show. So that was exercise 1. Do it again, step for step, and do all the steps. Then I go to exercise 2. And here we still are in the same world in some sense. But we get some new information here, and let's write it. The empirical average and the empirical variance of the numbers or random variables x1, x2, xn can respectively be written as xn bar, the empirical average, equal 1 divided on n, sum over xi, I equal 1 to n, as we have seen many times before. And the empirical variance is on the formula 1 divided on n minus 1 times the sum I equal 1 to n, xi minus xn bar, the empirical average, in the power of 2. Let also A and B be constants, and we define set equal AXI plus B, for E equal 1 to n in this exercise. So we will use that set is equal this. The first we are going to do in A is to show that the empirical average of the set are equal A times the empirical average of the x's plus B. Okay? If we are going to show the empirical average of the sets, we have to use the formula for it. So we know that 1 divided on n, sum over I equal 1 to n set I, that will give us the empirical average of the sets. But now we replace the set I with what's in the green rectangle, because set I can be written as AXI plus B. And here we can recognize something we did in exercise 1D. From exercise 1D, we know that the sum AXI, I equal 1 to n, plus B is equal A sum xi, I equal 1 to n, plus nb. So let's use that. So then we get 1 divided on n, that's this one. But then this can be written, as told just to the right here, as A sum over xi, I equal 1 to n, plus nb. And this should be multiplied with 1 divided on n. Okay. And then it's not very much more to do otherwise than multiply 1 divided on n into the parenthesis. So we get this to be equal A times 1 over n sum xi, I equal 1 to n, plus 1 over n times nb. And then we see that this first term can be written as A times the empirical average of the x's. We can see this here. The empirical average is 1 divided on n, the sum of xi's. So 1 divided on n sum xi's is this one. And here I can do like this, and we get b. So the answer is A times x bar n plus b, which was what we was supposed to show. But the remark, you have to understand exercise 1D before you can do this one. B. So here we are going to show that S set in the power of 2 is equal A in the power of 2 times Sx in the power of 2. Where S set in the power of 2 is the empirical variance of set 1, set 2, and so on until set n. So let's start. How can we write the variance of the sets? Well, we know the general formula for the empirical variance. That is 1 divided on n minus 1 times the variable we are dealing with, which is this time the sets, set I, minus the average of these sets in the power of 2. And we know from exercise 2a that set n bar is equal a x n bar plus b. We see this here. So then we can replace the set I. We can write that too, and we remember that set I is equal a xi plus b. So then we replace set I with a xi plus b minus, and we replace set bar n with a x bar n plus b in the power of 2. And then we get 1 divided on n minus 1, a xi plus b minus a x bar n minus b in the power of 2. And then we see that the b's cancels out, such that what we got now is just 1 divided by n minus 1. I forgot a sum sign here. I put it on here now. That should be obvious. So the sum here, e equal 1 to n, and the sum here, e equal 1 to n. And then we get the sum I equal 1 to n, and as I said, the b cancels out, such that we now got a xi minus a x bar n in the power of 2. So we are closer. I equal 1 to n, and then I see that a is common in both the terms in the parenthesis, so I put this outside a parenthesis like this in the power of 2. And now remember that a times b in the power of 2 is equal a in the power of 2 times b in the power of 2. So this gives actually that we can write this as a in the power of 2 times b, which now is xi minus x bar n in the power of 2. So a in the power of 2 is just a constant, and therefore I can put it outside the summation sign like this. In the power of 2. So, and if I just change a little here. A in the power of 2 times 1 divided on n minus 1. This is no problem. 3 times 2 is the same as 2 times 3. So, and now we see that this actually is nothing else but the empirical variance of the x's. And this is what we were supposed to show. That the empirical variances of the z's is actually the empirical variance of the x's times this constant a in the power of 2. So that was b, and then we can do the last, is it the last one? I think c in exercise 2. So let's do it. And now we should take it a little more easy here. Define, or we define UI equal xi minus x bar n divided on xx. This is so-called standardized variables. So-called standardized variables. Standardized variables we get when we minuses the mean and divide on the standard deviation. And that is what we are doing here when we are creating these UIs, which are the standardized variables. Okay. Comma, where Sx is equal square root of Sx in the power of 2. Which is equal to the empirical standard deviation. Okay, just a remark. And now we get to know what to do, or what we are going to show. We are going to show following. Show 1, that the mean of the u's are equal 0. So the means of standardized variables is always 0. Okay, and the second we are going to do, that is to show that the standard, variance, empirical variance of the u's are equal 1. So let's start with 1. So we know that the mean of the u's are equal, the sum is equal 1 divided on n, the sum over the ui's from I equal 1 to n. This is the normal formula for the mean. But now instead of writing ui, we can replace it and write this as 1 divided on n, sum I equal 1 to n, xi minus x bar n divided on the standard deviation of x, like this. And then we get 1 divided on n, and this Sx is actually just a constant which we can take outside the summation sign. So we get 1 divided on n times 1 divided on sx, sum I equal 1 to n, xi minus x bar n. And now let's write this out and change the factor 1 divided on n with 1 divided on n, because that don't change the result. As I said earlier, 2 times 3 is the same as 3 times 2. Sum, and now we don't write the sum, but we write the sum in its respectively terms, x1 plus minus x bar n plus x2 minus x bar n plus, and then when I is 3, x3 plus minus x bar n, and in the end plus dot 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 plus xn minus x bar n. And rearrange here, we get 1 divided on sx times 1 divided on n, parenthesis, x1 plus x2 plus x3 plus dot 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 plus xn. Here I have collected the x's, and then I write up all the xn bars, which is 1 for each term. So we get minus xn bar, minus xn bar, minus xn bar, minus dot dot dot, minus xn bar. And now we are going to study this a little closer. First of all, we get now x1 plus x2 plus x3 plus dot 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 plus xn, and then we have n terms of x bar n, so we get minus n terms x bar n, parenthesis. Okay, and then we have 1 divided on sx times 1 divided on n, and it's many ways to Rome, but we take this one today. x1 plus x2 plus x3 plus dot 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 plus xn, and instead of writing and minus n, and instead of writing x bar n, we rewrite that as the same as x1 plus x2 plus x3 plus dot 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 plus xn divided on n. You know that this we know actually. We know that this one is this one. The mean of the x's are the sum of the x's divided on n. So I replace x bar n with the sum of the x's divided on n. And why is that smart? Here, that's because we get now x1 plus x2 plus x3 plus dot 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 plus xn, and we can see that n can cancel out with n in that way, and then we have minus in front of this last term here, so we get minus x1 minus x2 minus x3 minus dot 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 minus xn, and then we see that what's in the parenthesis is actually equal 0, because x1 cancels out with x1, x2 cancels out with x2, x3 with x3, and xn with xn, and we get 0. And then of course if we multiply something with 0, we get 0. So that was what we was supposed to show. Yes. And then we have to do the second part, which is showing that the standard or that the empirical variance of the UIs are equal 1. So we are now showing this one. This we have shown, and this we are going to show now. So since we are going to find the empirical variance of the U's, we have to use the formula for the empirical variance. And the formula is 1 divided on n minus 1 times U, the sum I equal 1 to n, parenthesis, UI minus U bar n in the power of 2. But remember from exercise from above that UN bar is equal 0. So instead of writing what I just write, I can write this like following: UI minus 0 in the power of 2. And that makes everything much easier, because now we have SU in the power of 2 equal 1 divided on n minus 1. The sum I equal 1 to n UI in the power of 2. So let's now we use that remember UI is equal xi minus x bar n divided on sx. So I replace this for UI and get UI xi minus x bar n divided on sx in the power of 2. And then we get this to be, remember, if you have a divided on b in the power of 2, this can be written as a in the power of 2 divided on b in the power of 2. And therefore, we now can write this this like xi minus x bar n in the power of 2 divided on sx in the power of 2. Just using the rule to the right. So now we are closer. And this, which stands in the denominator here, sx in the power of 2, is just a constant. So we can write this as 1 divided on n minus 1 times, and I just take outside a constant, 1 over sx in the power of 2, sum I equal 1 to n xi minus x bar n in the power of 2. And as we know, we can change 1 divided on sx in the power of 2 with 1 divided on n minus 1 and write sum I equal 1 to n xi minus x bar n in the power of 2. And then we just have to recognize or to see that all this is nothing else but the empirical variance of the x's, sx in the power of 2. This formula stands in the text in the start of the text of exercise 2. We can go all up and see it. Here we have the formula for the empirical variance of the x's, and this formula is just what we got down here. 1 divided on n minus 1, the sum over the xi's minus the x bar n in the power of 2. So the desired result should be 1, and of course, and we got 1 now because here it stands x in the power of 2 divided on x in the power of 2, and with other words, the empirical variance of the ui's is equal 1. Cool? Yes, a little. So then this was the first video, exercise 1 and 2, and now we are going to make another video with exercise 3 and maybe 4. So do it again, and I see you soon. Bye.